So in this section, what we're going to discuss is the kernel and the range of the transformation. So we've been talking about linear transformations and how what they do is they transform entire spaces. They transform every vector inside of the space. Sometimes along a certain set of rules, sometimes, in ways that are maybe a little bit more unpredictable, but there is a certain kind of transformation that's occurring. And what we want to now do is kind of dive into a way to generalize, okay, what's happening to a space. All right, along two very important lines. All right, the first here is this idea of the kernel of the transformation. So the kernel of the transformation is the set of all vectors v belonging to v that map to the zero vector. So the kernel of t, we say, is going to equal to all v belonging to v such that t of v equals 0. And if you're looking at that, you probably should think to yourself, okay, so this looks familiar. So this looks familiar. Doesn't this look a little bit like ax equals 0? Right? Or the null space of A, if you want to think about it from that perspective. Well, it really does. Okay? If you think about it, if T gets represented by a matrix for the transformation, then AX equals 0 and the null space of A are going to be equal to, they're the same thing as the kernel of T. And in fact, they really pretty much are. And for our purposes for this class, they're going to be pretty much the same thing. Okay? Let's take a look at an example of how this might actually work. All right? So let's say, for example, we have a transformation T, and it's going to go from the set of all second order differentiable functions to first order differentiable functions. And we're going to say T of y is going to equal y double prime plus y. So what is going to happen here is we're going to transform y double prime plus y into a homogeneous function, right? We're going to set it equal to 0, right? And that's, T of v equals 0. So that's what you do, right? You set whatever you've got for the transformation, you set it equal to 0, and then you're going to go solve. And if we do this, right, what we're going to end up with is we're going to end up with y equals c1 cosine t plus c2 sine t. And so that's what the kernel of t is. It's c1 cosine t plus c2 sine t, c1, c2 belonging to R. That's it, okay? Right? Those are going to end up being like the solutions to your differential equation. And so consequently, that's the kernel of t, right? The solution to that homogeneous differential equation. Taking something a little bit more familiar, let's say, for example, we have t r2 to r2. So t of v, we're going to define it as t of x1, x2 equals 3x1 minus x2 and 2x2 plus x1. So our kernel of t is going to be basically this statement, which is the solution to 3x1 minus x2 equals 0 and 2x2 plus x1 equals 0. Okay, that's giving us back the 0 vector. When we solve the equation, what we're going to do is we're going to find that x1 equals 0 and x2 equals 0 is the only solution. So the kernel of t is equal to the 0 vector. So let's take a note that t, that our transformation from R2 to R2, has this matrix of the transformation of A equals 3, negative 1, 2, 1. So the kernel of t is also the solutions to AX equals 0. And after row reduction, we get that RREF of A is going to equal the identity. So AX equals 0 has only the trivial solution, so the kernel of t is equal to 0. So this is the other way to think about exactly what we just did, right? And in fact, if we can find a matrix for the transformation, finding the kernel is actually quite easy because all it is it's solving AX equals 0, which at this point in time you've probably done, 500 times. So let's take a look at another example. Here we have t r3 to r2, and it's given by t of x equals ax, where a is equal to this matrix, right? Negative 1, 8, 0, 2, negative 2, negative 5. When I row reduce, what I get is I get RREF of a is 1, 0, 35, and 0, 1, 5 halves, right? So the solution to ax equals 0 is the kernel of t. And so if I look at this matrix, what that's going to tell me is, okay, that the kernel of t is going to end up equaling the set of all vectors v belonging to v, such that we have t times, such that v, equals t times negative 35 negative 5 over 2, 1, okay, for t belonging to the real numbers, right? So basically, all of the vectors of the form, right, v equals all the vectors of the form t times 1, not 1, excuse me, negative 35, negative 5 halves, and 1. And there it is, okay? And that's your kernel of t. So, how do you find the kernel of t? Well, what you're going to have to do is you're going to have to set the transformation equal to 0 and solve. All right, that's basically it. Just like how do you find the null space of A, right? You set AX equal to 0, solve, right? That's exactly what we're going to do. All right, and it becomes especially easy when we can turn the transformation into a matrix, because then we're just solving AX equals 0 again. The second concept that we're going to look at now is called the range of T. So the range of a linear transformation T, V into W, is the subset of W consisting of all transformed vectors of V. All right, and so this is very similar, in fact, it's pretty much identical to the idea of range that we get from functions. Okay, so I've got over here, I've got my domain V, and I've got my range, or my codomain W, okay, and within W, I'm going to have the range of T. The thing about it is that when we talk about range from a linear transformation standpoint, the range of T doesn't actually have to be all of W. It might be only a subset of W. Okay, it might only be a subspace within W. In fact, it'll always be a subspace, but it may not actually be all of W. And so we have to be kind of like, we distinguish between W, right, which is the codomain, and the range of T. Those two things are actually different. So let's talk about that actual difference. So let's suppose that we have a transformation T, x1 to x2, and what we get is that T of x1, x2 equals x1, x1, x2, all right? So what I see here is the transformation, its domain is going to be in R2, and its codomain is going to be in R3, okay? Now, let's talk about what that means from a range perspective. Well, the vectors 1, 1, 2 and 2, 2, negative 3 are in the range of T, right? Because we have if x equals 1 and x2 equals 2, then we have 1, 1, 2. Or if x1 equals 2 and x2 equals negative 3, we have 2, 2, 3. However, a vector like 2, 0, 2 is not, because only vectors of the form A, A, B are in the range of T. So the question that we want to ask ourselves is, what is in the range of T? Okay? Because it may not be all of R3. It could be, for example, a one-dimensional subspace of R3, a two-dimensional subspace of R3. It could be all of R3, or it theoretically could be the zero vector, right? If it in fact turns out that our transformation transforms everything into the zero vector. All right, so let's take an example. Suppose that T, R3 to R2, is defined by, and we've seen this matrix before, it was the one of the last examples. T of x equals ax, and a equals negative 1, 8, 0, 2, negative 2, negative 5. So the range of T is going to be the set of all b belonging to R2 such that ax equals b has a solution. Basically, the idea is that if I take a vector, right, in this case a vector in R3, and I take it over to something, I mean, what is it that it's going to get in R2? What are all the values in R2 that I can actually get from this transformation, right? Like, what happens? So another way to see this is that the range of T is going to be the span of the column vectors of A. Thus, if we have a matrix A for T, then the range of T is going to equal the call space of A, right? Basically, what we're looking at is we're going to say, okay, well, what are the vectors that I can get with these three? What are the vectors in R2 that I can get with all those three vectors, right? Okay, and that's essentially asking the question of what's the call space of A, right? So if I go in here and I row reduce, I take the RREF of A, right? I've got a pivot here and a pivot here, okay? And by our definition of call space, that means that negative 1, 2 and 8, negative 2, right, make up a basis for our call space, right? So our call space is actually the span of these two vectors. What are the span of two linearly independent vectors? It's all of R2. okay? So essentially what the range from a theoretical standpoint is it's the set of all output vectors that we can get, right? Okay, from a linear transformation. And essentially, if we have a matrix that represents that linear transformation, that's going to be just the call space, right? It's just going to be all the linear combinations of the column vectors of A. So let's take an example. We've got T of V equals AV for T from R3 to R3, where A is going to equal this matrix. When I go out and I take the row reduction of this matrix, what I end up with is the identity, I3, okay? So if I look at this, I ask myself, well, what's the call space of A? The call space of A is going to have a basis of 3, 1, 2, 5, 2, 6, and 1, 1, 7. Okay? Which is equal to all of R3. Which makes a lot of sense given the fact that what we see right here is we have an invertible matrix, right? We've taken the row reduction of A, we've gotten the identity, it's invertible, and we know from the invertible matrix theorem that the call space of A, okay, if it's equal to the entirety of the space, right, if it spans R3, then the matrix is actually invertible, okay? Now what this means then too is that the range of T is just equal to R3. And that's it, right? We can get every vector within R3. Range of T, call space of A, pretty much synonymous. They're just, it's like an addition of it's like an added idea. The added idea of the transformation, right, being this function, and what we can get from that function is every single vector in R3. So that T, R3 to R2, and we have T of V equals AV. And this is the one where we saw that the kernel of T was V belonging to V, and it was like a group of these vectors, and it had the one vector T times negative 35, negative 5 halves, 1 inside of it, and the range of T was all of R2. So the kernel of T, right, okay, the kernel of T was this one-dimensional subspace of R3, okay? Notice vectors in R3, it's got the one dimension in there, okay? So there's our kernel of T, okay? One-dimensional subspace of R3. What you can think of is you can think of these vectors in the kernel, they're all going to map, everything in there is going to map over to 0, right? So basically what's going to happen is I say that it collapses down onto 0, right? Okay, it's a term some of my math professors used. I don't know if it's a mathematical term, but like that's the idea. It's going to collapse down onto 0. That entire one dimension goes from one full dimension to 0 dimensions. Then the other two dimensions here in R3 are going to go over onto R2. So we've got a V here and we've got a W out in R2, okay? And so we've got two dimensions here in R3, and they're going to map over here to two dimensions in R2. And then the third dimension, which is our kernel, is going to map down onto the 0 vector, right? And the reason why we're going to get all two of those dimensions, why we know that, okay, a further one, is that it turns out that the range of T is the entirety of our codomain, okay? The range of T is all of R2, our codomain. And so what the kernel and the range help us to do is they help us to think about what's happening under a linear transformation, right? With our, say for example, our domain. What's going to occur with our domain? We're going to take everything in the domain, right? Because if we can't take everything in the domain, we don't have a well-defined transformation. So we're going to take everything inside of the domain, and it's either going to be mapping onto 0, or it'll be mapping onto the range, okay? And basically, and we're going to get into this in just a second, this is going to kind of, inform our thinking, that those two dimensions that are going to be mapping onto the range, plus the one dimension, gives me all of the different dimensions that are in my domain, right? And that's going to actually inform the next thing that we're going to talk about, which is the general rank nullity, right? The idea that our domain has to map onto something, okay, what is it that it is going to be mapping onto? So now if we consider a second one, we can see a similar kind of thought process. Now we have the kernel of t is equal to 0. So all I have is the 0 vector here, okay? And then I have the 0 vector over here, right? And that's what that's saying. That's saying that the only thing that maps over, right, okay, here's the kernel of t. The kernel of t is over here in the domain, okay? And it maps over here in the range just over to 0. So the kernel of t goes from a 0-dimensional subspace to a 0-dimensional subspace. Then my range of t is R3. Okay, so it's all of R3. Okay, that's my range of t. So in this case, R3 over here, it's 3 dimensions, and its 3 dimensions are all going to map over into the range. So we're going to go 3 dimensions in R3 in our domain over to the 3 dimensions inside of our codomain. Okay, so basically we're going to kind of like, it's kind of a perfect mapping here, right? The kernel of t is only going to map over to 0, and then all of the range of all of the domain of t, R3, will map over to all of the codomain of t, which is also R3. So this brings us to our general rank-nullity theorem. So if T is a vector space V onto W, it's a linear transformation, and V is a finite dimension, and V is finite dimensional, then the dimension of the kernel of T plus the dimension of the range of T equals the dimension of V. Okay? And so this should look pretty much, or we should be able to transform this pretty much into a similar statement from our other rank-nullity theorem. We know the kernel of T, so if we write the kernel of T is the null space of A. Okay, so we write that's the dimension of the null space of A. Plus, and then we know the dimension, basically, of the call space of A. And that equals here in N, right? This is for matrices A. Now, the null space, okay, we call that's called the nullity. The dimension of the null space is called the nullity. Plus, and the dimension of the column space, if you kind of remember, the dimension of the column space is going to be equal to the number of pivots that we have in the row reduction of A, right? Well, what's also equal to the number of pivots in the row reduction of A? The rank of A. And that'll equal N. And there you go. So you can see, here's general rank nullity, utilizing our ideas from the kernel of T and the range of T from linear transformations, and how it actually fits or matches up with the ones from our matrices A. So let's take a look at some examples. Suppose we have T and it goes from R3 onto R2, and we have the kernel of T, again, is this one-dimensional subspace of R3, and the range of T is equal to R2. So V equals R3, and so the dimension of V is going to equal 3. The dimension of the kernel is going to equal 1, because there is one vector in the basis for the kernel of T. Okay, so that's the dimension of the kernel of T. And the dimension of the range of T is going to be equal to the dimension of R2, which is 2. So 2 plus 1 equals 3. Rank nullity is confirmed. Or suppose we have this other linear transformation. We go T, R3 onto R3. The kernel of T is equal to 0, and the range of T is equal to R3. So now the dimension of the kernel of T is equal to 0. The dimension of the range of T, right, is going to equal 3 because it's R3. And the dimension of R3 is going to equal 3. So 0 plus 3 equals 3. And our rank nullity is confirmed. The proof of this theorem is in the book, and it is worth looking at and reading. For the purposes of what we're going to do throughout the rest of this video is I'm going to take a look at some ways that we use rank nullity in order to say some things about the matrices or about the linear transformation. So let's take a look at some consequences of the general rank nullity. So suppose that T, R4 onto R4, and kernel of T is equal to 0. Is the matrix of the transformation A invertible? Okay, so one thing that I want to notice is I want to notice that T, okay, right, is a transformation that goes from R4 to R4. So V, in this case, our domain is R4. And the dimension of V is equal, again, to R4. Okay? Now, there are a couple things that I might want to notice about here too. In a previous section, we talked about how big is that matrix, right? So if we think about A, the matrix for T will be 4 by 4. Okay, it's going to take vectors in R4 into vectors in R4, and so if you kind of shape that, that's going to end up being 4 by 4, right? Which means it is squared. Okay, then we can also say, oh well, that means that the kernel of T, okay, is going to equal 0, implies that the null space of A is going to equal to the 0 vector. All right, and by the invertible matrix theorem, A is invertible. We can use rank nullity also to show that the call space of A is going to end up being all of R4, right? So by rank nullity, we have the dimension of the kernel of T, 0, plus the dimension of the range of T will equal the dimension of V, which equals R4, or excuse me, which equals 4. Dimension of V equals 4. So what that means is that the dimension of the range of T is going to equal 4. So if the dimension of the range of T equals 4, all right, and it's in a 4-dimensional space R4, that actually tells me that it's got to be all of R4. So the range of T equals R4. It also means that the call space of A equals R4. So just noticing that the kernel of T equals 0 tells me an incredible amount about this particular matrix. One, I'm going to pay attention to my domain and my codomain, right? Because what that does is that tells me the dimensions of the matrix. In this case, 4 by 4, so it's square, right? Square matrix means that I can use the invertible matrix theorem. If it wasn't square, I wouldn't be able to, all right? But given that I can use the invertible matrix theorem, knowing that the kernel of T equals 0 implies that the null space of A equals 0, because the two are basically synonymous. And then by the invertible matrix theorem, A is invertible. Or conversely, we might actually look at the rank nullity theorem, and we say, okay, well, the dimension of the kernel of T is 0, plus the dimension of the range of T, well, that's my unknown, okay? That's going to equal 4, because that's the dimension of V by rank nullity. So my range of T is going to equal R4, because the dimension of the range of T is 4. So my call space of A is going to end up equaling R4, okay? And it takes some thought. You kind of have to like connect the dots between all of the ideas, but if you can do that, all right, you've actually found out an incredible amount about the transformation and all about also about the matrix A. Now let's suppose that I have a transformation that goes from P3R to R3. The question is the kernel of T only the 0 vector? Okay, and so I'm going to use rank nullity in order to figure this out. So V is equal to P3R. And that's the set of all third degree polynomials. Okay, the set of all third degree polynomials. And so its basis, its standard basis, is S equaling, and it'll be 1x, x squared, and x cubed. So P3R is 4-dimensional. So the dimension of V is equal to 4. Now, here's the thing. If we think about this, the range of T has to be less than or equal to 3 because range of T is in R3. Okay? The range of T is the set of all vectors that I can get utilizing my linear transformation. It can't be bigger than the codomain. I can't have more dimensions than the codomain. All right, so consequently, the range of t has got to be limited. It's got to be less than or equal to 3. Okay, so if I think about this, right, what that means is that I have the dimension of the kernel of t, okay, is going to equal has got to be greater than or equal to 4 minus 3, which equals 1. And the reason why is that this is the dimension of V, and this here is the maximum size of the range of T. So the dimension of the kernel of T has to be greater than or equal to 1. And what that means is that the answer is no. Because the kernel of T must be greater than or equal to 1. Or dimension of the kernel of T, excuse me. By Rank-Nullity. So it's just a little bit of logic. One, we know that P3R is 4-dimensional, okay? And the range of T then is going to be less than or equal to 3 because the range of T is in R3, okay? So it's a subset or a subspace of R3. It could be all of R3, which is fine, but it doesn't have to be. What that means is that the dimension of the kernel of T has to be greater than or equal to 4, right? The dimension of V minus that maximum size of the range, okay? Because of the rank nullity. So that means the dimension of the kernel of T has to be greater than or equal to 1, okay? And hence, what that means is that because the dimension of the kernel of T is greater than or equal to 1 by rank nullity, okay, there is at least one vector in the kernel of T. Okay, it can't be the 0 vector. The 0 vector has 0 dimensions, so consequently we have to have at least one vector in there. Okay? All right, so in this lesson, what we've talked about is we've talked about the kernel of T, which is essentially synonymous to the null space of A. We've talked also about the range of T, which is pretty much synonymous to the call space of A, and the General Rank-Nullity Theorem, which is pretty much the same as the Rank-Nullity Theorem that we learned in Chapter 4. And this kind of underlines or underscores the fact that working with linear transformations is pretty much very similar to or the same as working with matrices, just like a different set of concepts, a different set of language, right, that allows us to think about and conceptualize linear algebra in a different way. Okay, so this completes the lesson.